Hi, I'm Jesus, and me and Michelle are on Team LeBron Tourage, and we will be presenting to you our Sprint 1. So our customer is the Toon Squad, and they're stuck in a virtual realm competing against an evil AI, and they need our help in order to create a robot that can complete several different tasks. These tasks include uh, pass, jump shot, and dunk, and it has to be able to complete those tasks efficiently, consistently, and also be easy for them to fabricate. For our first design, we named this the Curry design, and that is because, as you can see here, most of the components are going to shoot the ball. The first task and the second task are almost identical, except they're just mounted at different angles. And you just launch the ball in there, and then the air does all the work for you. For task three, the balls fall down into the catapult, and then the solenoid releases it, and then we'll get more into this design on the next slide. Some pros is that pneumatics can be great, but it also has its drawbacks, and I'll talk about that in a little bit. But um, also, since we have two pretty much of the same components, fabrication would be really easy for this one. We just have to make two identical components. And then also the mount for the jump shot provides fine tuning for us, and then also it just looks cohesive since there's two of the same things on there. The cons, it lacks consistency. Um, the jump shot PVC can just has too many drawbacks, and then also the mouse trap can be very sporadic. So there has to be many connections within the pneumatics itself, and just anything can go wrong at any given time. And then on the next slide, we'll get onto the next design. This one is called the hardened design, and as you can see, task 2 and task 3 look kind of um, almost simple, and then task 1 is just too extra, and it's out of place with the rest of the design. And on the next slide, we'll get into this more. Some pros is that pretty much the only pro is also the biggest drawback is that the pneumatic pass can be very effective and consistent, but the setup time for this by itself for that one task would just take too long. And then also, like I mentioned before, the dunk solution can be very inconsistent just because it's a mousetrap launching three different balls at the same time. And then on the next slide, we'll get into the different design. This one we named for Westbrook, and it's just because it's based off of like technique, like it should work, but it could ultimately just proves to have low accuracy because of different variables. So for the first, you can see that on task one, it's just a ramp. It looks simple, but I'll get more into that on the next slide. And then PVC, same thing that we've had on previous slides. And then on task three, you can see that this is a mobile design, and it would just we collect the balls, and the balls fall into the little slot, and then the ramp would just telescope out over the dunk zone and just drop the balls in there. But we'll talk about some cons on the next slide. So some pros first is that it's simple fabrication. It wouldn't take too long. We've already designed some PVC stuff, so we have all the components there. And then the telescoping ramp can just be very effective because it dumps the balls right over the top. And the pneumatic mounts also allow for fine tuning. The cons is that like I mentioned before, for the other designs, it's too inconsistent. The PVC is. Um, Too many variables can go wrong here. Just like when the balls are supposed to fall into that, what you can see there labeled as fork one, they could bounce out. And then the mousetrap, which would theoretically be used to push out the telescoping ramp, it could be hard, it could prove difficult to implement that. Um, and then also the angled ramp can just introduce new variables like swirl coming off the ramp and stuff like that. And on the next slide, Michelle will talk about our actual preferred design.
So our preferred design is called the King, which is named after LeBron James. So here's just an overview of the final design, and we'll get into the detailed views of each task in the next few slides. So for pass, we just have a simple straight ramp that is at a fixed angle mounted on a 3D printed part. There's a small solenoid. which releases the ball, which will then roll down the ramp and using gravity will hit the bucket, completing the pass. Next, looking at into jump shot, we have a rubber band slingshot, which is mounted with a swivel mount to control the angles for the launch. Here on the side view, the rubber bands will be hooked here. Oh, the rubber bands will be hooked here, and then the solenoid will retract once initiated, and the ball will be propelled forward and hopefully landing into the bucket. So next at Dunk, we do have multiple parts going on here. This unit is mobile, so that is something to take note of. So first, the robot will move forward and hit down the PVC pipes. So the two top slits here will hit down the taller ones, and the bottom slit here will hit down the one at a less height. Once the PVC pipe is hit, it will then fall into the ball collector over here. Then using a pulley system and a motor, the slide tracks will extend and the ball collector's trapdoor will be released over the dunk zone, releasing the balls into the cups. Next, looking at the control system algorithm for the King, we first have launch, which is just with a push button. The red here symbolizes that the robot is stationary, while green symbolizes that the robot is mobile. So after launch, the solenoid for the ramp is then activated, which will retract, and the ball will roll down the ramp and complete pass. Then the solenoid for jump shot is also activated, and the rubber band will then hit the ping pong, propelling the ball forward. Next, the robot is now mobile for dunk. So a large motor will then turn, which will turn the gear, which will turn the axle, and then finally the wheels. The robot will move forward, collect the yellow ping pong ball and the money balls with the fork. After that, the robot is stationary and the small motor will cause a pulley system to extend the slide tracks, and the box will also be open with the trapdoor using that pulley system. Finally, all the operations are terminated. So looking at the concept evaluation matrix, you can see that it was very close between all of our 4 designs. However, the King did come up on top with a relative total of 0.858. So 2 criteria I'd like to point out which hold relatively high importance are accurate actions and consistent operation. So the King both had the highest scores for both of these compared to all the other ones, which is very, very important. So looking ahead in fabrication, we do stay under the $100 budget at $60.87. The most expensive thing that we have is the caster wheel of $10.96. Here's just a list of our 3D printed parts and our laser cutted parts and the production time of 992.5 minutes for all of our pieces. So for testing, we want to determine consistency and accuracy values. We want to do exhaustive testing with a lot of trials for each task. For the pass and jump shot, we will test different angles. For the jump shot, we will test different number of rubber bands to see what gives us the right amount of energy. We will also replace each of these rubber bands after 10 trials. For the dunk system, we will just determine the average number of points attained for each trial. In conclusion, some anticipated challenges we expect is the integration of all components onto the robot frame. There are a lot of parts, and no part is kind of shared between each task, so that is something to account for. Also, the weight distributions due to the slide tracks is something that we need to pay attention to because we don't want our robot to tip over. Lastly, we want to ensure our robot performs each task accurately, which is something that we face difficulties with in our first sprint. And that is all. Thank you for listening.